Hello, my name is Winter, and this is part 2 of my video about hyperoperations. The hyperoperations being the operations such as addition, multiplication, exponentiation, and so on, which we denote with square brackets with numbers inside. So square bracket 1 is addition, square bracket 2 is multiplication. And the process of going from, say, addition to multiplication, or any hyperoperation to the next, is called expedition, which is a term I coined last time. So what we're going to be doing in this video is using these three main properties we found about all the hyperoperations in the last video in order to find a consistent definition for the zeroth hyperoperation that keeps some of the properties that all the other ones do. So essentially what we're going to be doing is taking an anti-expedition, whatever that means. We're going to be using this operation a lot for this video, so it needs a name and a symbol. This operation goes by many names, but for this video I'm going to be calling it zeration, because it is the zeroth operation. And for its symbol, I will simply be using a vertical line. So A, vertical line B, is A zerated with B. As we learn more about zeration, we will be filling out this table at the bottom right here. And eventually, hopefully, we will have all of the possible values for A zerated with B. So as I said, we're going to be using the properties down below to figure out more about zeration. So let's start with the second property. So A operated with A is A operated with the higher up operation with 2. Now this is, we said, only true for W greater than or equal to 1, but that's only because we have not defined zeration yet. So let's extend this to W equals 0 for zeration. So let's fill that in now. A, 0 is zeration, so bar A equals A. If we plug in 0 for W, we get 1 here, and that's addition, plus 2. So, for any value of A zerated with A is A plus 2. And now, we can fill in the diagonal of our table, because if we plug in 0 for A, it's simply 0 plus 2, or 2. So, we can go along our diagonal and add up the value by 2. Now it may seem abrupt, but we're actually already done with everything we can do with the second definition at this point. Really, there's not too much you can glean from just this alone, but that's okay. We have the big boy, property number 1. Now let's extend this in the same way we did number 2. Once again, we have W greater than or equal to 1. Let's extend this to W equals 0. So A, W plus 1, 0 plus 1 is 1, so plus B equals A, 0, W is 0, so var A, W plus 1 is 1, plus V minus 1. So now we have another equation, but it's not quite in the form we want. What we want is to solve for A var some other number C. It could be B, but really we just want to be able to have this equation in terms of addition, since that's what we know how to do. So let's simply sub in some number C for this value. Then we'll have A zerated with Z on the right. So let's let C equal A plus B minus 1. So this also happens to mean if we solve for B in this equation, B equals C minus A plus 1. So let's plug these two formulas into the equation to get rid of B. A plus C minus A plus 1, remember that's what we solved for B, equals A var C, which is exactly what we wanted. But we can cancel on this side the A's. So C plus 1 equals A zerated with C. A zerated C equals C plus 1. Now what we've just found is an equation for any two numbers A and C. We can find their zeration. But we have to be careful when we make substitutions like this, because A and C may not be independent. And what that means is, let's say we had our older equation, our other equation we had A bar A equals A plus 2. Remember this one from a little ago? What if we just said C equals A? We plug in C, voila, a bar c equals a plus 2. We can fill in the whole table. See, we can't do that because c is just the same as a. They're not independent. And what that really means is, given a value of a, we cannot get any value of c. So we want to make sure that for this equation, given any value of a, we can achieve any value of c so that this applies to every single number. Basically, given that a is a naught, so a0, some fixed value, maybe it's 2, maybe it's 3, given a is one specific number, we want to show that for any number c naught, c can create c naught. So maybe if we have a is 2, we want to show that c can be 3 or 5 or anything. We want to show that for any number a, c can be anything. So let's look at our equation. We said c is a plus b minus 1. Now if we say that a is a naught, then we have this equation. Can we make this equal to any number c naught? Well, remember we have this variable b. B can be anything we want, because at the very beginning we already knew that a was independent of b. We kind of accepted that. For any numbers a and b, this is true. So let's just let b equal c naught, equal something that will create c naught. So let's solve for b in this equation. So b is c naught minus a naught plus 1. So if we plug in that into this equation, the a naughts will cancel out and the 1s will cancel out, and c will equal c naught. So indeed, no matter what value we choose for a, we can get c. And just to show this with a more concrete example, let's do the a equals 2, c equals 3, 1. So given that a is 2, we know that c is 2 plus b minus 1. We want to be able to achieve any value c naught. So the 2 and the 1, we get b plus 1 equals c naught. And then we see that b is just c naught minus 1. So we can plug in c naught minus 1 for b, and we will always achieve c naught with c, even though a is fixed at 2. So a and c are independent. So now with this equation, since we've proven that a is independent of c, we can fill in our entire table, which is great. But there is a problem. Maybe you've seen it already. But let's just say that c is equal to a, in this case, since it applies to all a and c. So this comes out to a z raised with a is a plus 1. But maybe you remember, we already found earlier from the second property that a z raised with a is a plus 2. And that's how we filled in this table earlier. So plugging in 0, the simplest value really, we get 2 different answers for 0, z raised with 0. Before we had it 0, z raised 0 was 2, and now it's 1. So where did we go wrong? It can be hard to find where you made a mistake. So let's go back directly to where the properties lead when you plug in w equals 0 to these two equations. So we must have made a mistake somewhere, so using these we should be able to find out what the true values of a z raised with b should be. So this is true for all a and b, so let's plug in b equals 1. So b equals 1, a plus 1 equals a bar a plus 1 minus 1, which is a bar a. But that's an immediate contradiction to the other property. But why can't these two agree? Well, in fact, this means that these two properties cannot coexist within zeration. Now, why is that? They coexisted in all the other hyperoperations. What's different now? As always, when asking the question of why in math, it can be hard to answer because when you get deep enough into math, you just have to accept something as true. There is no more why. But I'll try regardless. It has to do with this third property we found of the hyperoperations. For all values of w greater than or equal to 2, aw1 is a. So that applies to a times 1 is a to the first power is a, and so on. But this is for w greater than or equal to 2, because a plus 1 is not a. But let's say for a moment that it was. So a plus 1 is a. Then, for this equation, plugging in b equals 2, a plus 2 is a bar a plus 2 minus 1 equals a bar a plus 1. And as we said earlier, a plus 1 is a, so this is a bar a, which agrees with this equation over here. And that's why these two properties agree for the other hyperoperations, but not for this one, because of this different property of addition. But then you can ask, why is addition different from the others? Essentially, it's because that's how it was defined, and that's how the hyperoperations were defined after. But then comes the question, which definition of zeration is correct? Which one is the right one? Well, like we talked about last time, there isn't really an answer to the what is right and what is wrong. Both of these have properties that we want from the other hyperoperations, but we know that there isn't a zeration that has both, or all of the properties we want. So, for the rest of this video, I will be looking at a bar b equals b plus 1, because our chart is more full on this side. Of course, there is more to explore with the other definition, using property 2, and I have some further exploration questions in the description about that, so I highly encourage you to explore those. Now that we have our definition and full table of zeration, let's make sure that it follows the properties that we want it to. Specifically, that addition is fast zeration. So let's look at an example. 2 bar 2 bar 2 is repeated zeration, but 2 bar 2, b is 2 in this case, so 2 plus 1 is 3. This is 2 bar 3, and 3 plus 1 is 4. Now 4, as we all know, is 2 plus 2. But from this equation, we can write 2 plus 2 as 2 bar 2 plus b is 2, so it's 1, or 2 bar 3. But 3 equals 2 plus 1. And we can rewrite that with this equation again as 2 bar 2 plus b is 1 this time, b minus 1 is 0, which is 2 bar 2. So 4, written as 2 bar 2 bar 2. Indeed, addition is repeated zeration. But let's look closer at this equation. 2 bar 2 bar 2 is 2 plus 2, but each time we evaluated the bar, we added 1. So it's 2 plus 1 plus 1. Let's look at this on a number line. 2, 3, 4. We started at 2 for our first number, and then we add 1 once, and then we add 1 a second time to get to 4. So 2 plus 2 is the same as adding 1 to 2 twice. This is just counting up by 1 a certain number of times to find the sum. So it makes sense that before addition would be counting, because addition is simply fast counting, as you've known since you were a kindergartner. But if below addition is counting, which feels right, it's very much the bedrock of math, then what's below counting? What is the negative first hyperoperation? Well, let's figure this out. Let's use the same property that we did to find zeration. And this time plug in w equals negative 1. So a, w negative 1 makes it 0. So a, 0v equals a minus 1, a, 0, b minus 1. So plugging in our symbols, we have a, bar b is a, negative 1, a bar b minus 1. Now we have a definition for zeration now. We just add 1 to the second number. So a bar b is b plus 1, and a bar b minus 1 just comes to a, and to b. So now we have this property for any two numbers, a and b, a negative 1b is b plus 1. But wait, doesn't this look familiar? That's exactly our definition for zeration. So, the operation below counting is still counting. Zeration is below zeration, and if you keep going down, you will get the same operation over and over and over again. Isn't that kind of cool? Truly, nothing is below counting in the hyperoperations. It is 0 and everything below. A few years back, I went through the same process of trying to find what the 0th operation is. I hadn't looked much into the hyperoperations at that point. I was just trying to figure out what it would be based on the other ones. And I ran into the same problems that we did here, trying to use these two properties at the same time. And that left me stumped for a long time until I eventually tried the problem again later and realized what I had done. So with this video, I wanted to convey that these non-mistakes can cause such huge problems. Just the act of assuming two things that you feel like should be able to be true at the same time simply can't be. When I created this, and when anyone explores math on their own, there's no sense of right or wrong. It's just whatever you create, and that's it. Maybe you have some goals about properties you want to incorporate to what you're creating, but sometimes that can't be done. So I wanted to give everyone who watches this a good idea of what it means to create your own math, to explore math in your own way. I feel like it's a pretty creative process that we don't get to see much in school. So I hope you enjoyed exploring Operation Zero and all the hyperoperations of it. I have some further exploration questions in the description if you're interested in learning more, or you can explore anything of your own on this, of course. Thank you for watching.